This theorem is very important one, and so many times this theorem is asked in the exam. So let's start with this theorem. This is a very important one. A mapping F of a matrix space X into matrix space Y is continuous on X if and only if F inverse V is open in X for every V open set in Y. Now suppose we are having a mapping F from X to Y, and this is two-way proof. One, if F is continuous, we have to prove that for any open set V in Y, F inverse V is open in X. This is the one way, and the converse also. If we are having every open set V in Y and F inverse V is open in set X, then we have to prove that F is continuous mapping, right? So let's start with the proof. Suppose F is continuous on X and V open set in Y is given. This is the first proof, one way. Suppose F is continuous on X and V is open set in Y. Just we need to apply the definitions for the open set, for the interior point, right? Just we need to take care of the definitions only and the proof will be over. Required to prove that F inverse V is open in X. This we have to prove. F inverse V open in X means what we have to prove? Every point of this open set is an interior point. This we need to prove. That means we have to prove every point of F inverse V is an interior point of F inverse V, right? This thing we need to prove. Let's take a point P from this F inverse V, right? So because we need to prove F inverse V as an open set, let's take a point P from the set. Let P is the element of F inverse V. Then, which means Fp is belonging to V. Take this F inverse on the other side. That means Fp is belonging to V. But V is an open set in Y, right? But that means Fp is an interior point of this V. This is the definition for the open set. So because Fp is belonging to V, that means, and V is an open set, that means Fp is an interior point of V. And when the point is said to be interior point of some set, if neighborhood of that interior point is belonging to V. Thus, there exists, we have to form the neighborhood for this Fp for epsilon positive such that I am having the neighborhood of Fp having the radius epsilon. That means this neighborhood is the element of V, right? Now since F is continuous at a point P, this is given to us. Since F is continuous at P, right? So let's apply the definition for this continuity then. So there exists delta positive such that what is the distance in Y? We are having the element F of X and F of P. See, Fp is the element of, if P is your element in X, then Fp will be belonging to Y. So Fx and Fp both are the elements of Y. So distances for Fx and Fp is less than epsilon. For What is the distance in x? We take the point x and p. And this distance is less than delta, right? Now this implies, see, distance between fx and fp is less than epsilon, means if we are having the neighborhood of fp with radius epsilon, this is the neighborhood we have formed here, this fx will belong to this neighborhood. Is it clear? See, you are having the neighborhood of fp, right? Suppose this is a point fp, its neighborhood is this, and with radius epsilon. Because here it is saying that distance between fx and fp is less than epsilon. That means fx will also inside this neighborhood. Then only the distance between these 2 points is less than epsilon, right? So whenever we are having the distances in y as less than epsilon, that means if we take the neighborhood of fp, which implies this fx is the element of this neighborhood. This is nothing but we are saying that fx is the element of neighborhood for fp. For here also we can say the distance between x and p is less than delta. Suppose I form the neighborhood of p with radius delta, that means x is also belonging to this neighborhood. Right? Clear? Now, thus what we have said, x belongs to the neighborhood of p with radius delta, implies f of x belongs to neighborhood fp with radius epsilon. Now neighborhood of p is a subset of v. See, neighborhood of fp is the element of v. This neighborhood of fp is contained in the set v. So from here we state this again and we say that this neighborhood of fp is subset of v. Clear? Which means f of x is the element of this v. Which means x is the element of, take f to the other side, f inverse v. Just see this like, see, x will belonging to the f inverse v from here. Now whenever x is belonging to some set, imply x is belonging to other set, that means that set is a subset of this set. So which implies delta neighborhood of p is a subset of f inverse v. Clear? Now that means neighborhood of p is contained in f inverse v, and neighborhood of p is an open set also. And whenever a point whose neighborhood belongs to some set, that means that p is an interior point of this f inverse v, because its neighborhood is contained in this set. So whenever neighborhood of any point belonging to some set, that means that point is an interior point of that set. So because neighborhood of p is a subset of f inverse v, that means p is an interior point of f inverse v. This we need to prove, but p was arbitrary, therefore every point of f inverse v is an interior point of f inverse v. Hence, now when every point of f inverse v is an interior point of f inverse v, means f inverse v is an open set. Clear? Let me revise this proof again. So this is a one-way proof. See, suppose f is continuous on x is given to us and v is open set in y. We need to prove f inverse v is an open set in x. For that we have to prove every point of f inverse v is an interior point of f inverse v. So I have taken a point P from this f inverse v. So I need to prove that P is an interior point, and because P was arbitrary, so every point of f inverse v is an interior point of f inverse v. So let's take P from this f inverse v. P element of f inverse v means f of P is the element of v. But v is your open set, and recall the definition for the open set. The point which belongs to the open set means that point is an interior point because V is an open set. The definition of open set says every point of the set is an interior point. So because Fp is belonging to the open set, that means Fp is an interior point of V. Alright. Now suppose we form the neighborhood of Fp. Because Fp is an interior point of V, it must be having some neighborhood which should contained in that V. As per the definition for the interior point, its neighborhood also belongs to the set V. So for epsilon positive, I mentioned the neighborhood for Fp with radius epsilon and it's belonging to V. Okay. Now what is given to us? F is continuous at P. Apply the definition for the continuity. There exists delta positive such that distances in y, fx and fp less than epsilon. For distances in x, xp less than delta. Now because the distance between fx and fp is less than delta, if we see the neighborhood for fp whose radius is epsilon, because the distance between these 2 points is less than epsilon and fp is having itself a radius epsilon. The neighborhood of Fp is having the radius epsilon. That means the other point belongs to this neighborhood. Clear? For if the distance between xp is less than delta, if we form the neighborhood for P with radius delta, that means this x is naturally, automatically is the element of this neighborhood P. Because distance between these two is less than delta. And P and the neighborhood of P is having radius delta. So obviously x is lying between lies in the neighborhood of P, right? Now from this statement, from this result, we say x belongs to neighborhood of P with delta, imply fx belongs to the epsilon neighborhood of Fp. And because this neighborhood is also contained in V, the open set, as Fp is the interior point of V, which implies this Fx is also the element for this V, which implies x is belonging to, take f to the other side, f inverse V. So from where we start, x element of this set, where we ends, x element of this set. The remark, that means this whole set is the subset for this f inverse V. Now the neighborhood of P, what we have gotten, neighborhood of P is a subset of this f inverse V. That means P must be the interior point of f inverse V because its neighborhood is contained in this. But P was arbitrary. We have taken any element P as. So P was arbitrary. That means every point of f inverse V is an interior point of f inverse V. And because as per the definition for the open set, f inverse V is an open set. Very, very important theorem. Now the converse part. Conversely, suppose f inverse V is open set in X. Suppose f inverse V is open set in X for every open set V in Y we have to prove that this f is continuous on P. So let we take the element P from X first. Let P is the element of X. Then f of P will belong to Y. Okay. Now, therefore, for every epsilon positive, let's take C. In Y metric space, we are having a open set V, right? For every open set V in Y. So we have to found an open set V in Y. V is open set. Let's mention that V as neighborhood of FP, because neighborhood of FP is belonging to Y. Let's make the neighborhood for FP with radius epsilon. Because every neighborhood is an open set, so neighborhood of FP is also an open set. Let's name this open set as V in Y, right? So being a neighborhood is open set in Y. I'm taking V as neighborhood of FP as an open set of Y. Clear? Okay. By hypothesis. Then by hypothesis, F inverse V is open in X, right? Because if we take this V as an open set in Y, it is given to us that F inverse V is open in X, where V is the neighborhood of FP with radius epsilon. Now, because F inverse V is open in X, let's take a point from here. So now P belongs to F inverse V. Because F inverse V is open, that means P is the interior point of F inverse V. Therefore, P is an interior point of F inverse V. Because P is an interior point of F inverse V, we must be having the neighborhood of P, which is subset of F inverse V. Right? Just recall the definition in every step. Thus, we have to make a neighborhood of P, then there exists delta positive such that neighborhood of P with radius delta is the subset of F inverse V. Now, since, okay, in the next page, I'm taking the point from this neighborhood. X is the element of, suppose I take the point X from this neighborhood. This will imply X belongs to F inverse V, because this neighborhood is contained in F inverse V. Have I written this? Yes, this neighborhood, because I have taken a point X from this neighborhood and this neighborhood is contained in F inverse V, that means that X is the element of F inverse V, which implies F of X is belonging to V, and V is what? Neighborhood of FP with radius epsilon, right? Which implies F of X is the element of this neighborhood. Clear? Which means, see, Fx is contained in neighborhood of Fp, having the radius epsilon. That means distance between Fx and Fp is less than delta. Same concept. This is, less than epsilon. See, the neighborhood of Fp, this is the point, right, having the radius epsilon, right, fx is belonging to this neighborhood. Okay, that means distance between these 2 points is less than epsilon. That's what I have written. Clear? So therefore we got the distance in y, fx, fp as less than epsilon for x belonging to this neighborhood, which means let's write the same concept for x and p also. Since if we having the neighborhood of P with radius delta and x is the element in that neighborhood, that means distance between x and P is less than delta. So this is nothing but the distance in x. This is what the definition for the continuity we are getting. Okay, but epsilon was arbitrary. Therefore, f is continuous at P. Again, but P was arbitrary. Therefore, f is continuous on x. Clear? Very easy proof, very interesting proof, and very important theorem. I am saying again and again. One more theorem with the same concept we'll be discussing in the next video. Thank you.